let me just point out that this homework is a killer, and if you haven't started on it yet, that's not good. Now, this homework is mostly a killer because it looks like a killer. It actually isn't. It's definitely going to take more effort, even if you know exactly what to do. Just the writing of the answers itself is going to be more than you've ever done. You may notice that there's one less question. Usually there's 10 questions, there's 9, because the 1 through 9 was enough, to be blunt. Okay, now what you're doing is you're doing as much as you humanly can with the wave functions. I know you just saw them, but the homework is written in a pretty self-explanatory way. It shows you what to set up, and you just have to do it. As usual, I actually was a bit more liberal with the cheat sheet, the equations at the beginning. Normally I like to put things like this, but I put a couple of really harder ones. I put them in the proper R and A naught form so that you wouldn't get lost. So I have 2 different ways of putting the cheat sheet equations at the beginning of problem set 8. I put some of them like this, like you find them online, but I did put a couple in the proper e to the minus r over a naught form, just so it just wasn't so bombastic. So that's why I did that. Okay. Now here's a heck of a thing that you should be aware of. And it's kind of the point of the homework, although I don't say it. But again, for you to understand what's going on, this is why we have these extra half hours. So on its face, you may be like, well, why are you asking that? You can still answer the question, but you may be like, well, why are you still asking that? I'm asking questions 1 through 2 are just a bunch of integrate the wave function questions. It's to show that it's normalized, but really I'm just getting you to integrate it. For one, calculus, that you should be able to do that. Number 2, if you are Googling what is the wave function, and I do this all the time, you have to be extraordinarily careful because you will find one of 2 answers. Here's just the 1s. And that's why I was flummoxed earlier about what the normalization constant was. Because there are 2 different sets of wave functions, radial wave functions. How is that possible? Right? That's really, really nuts. So how can there be 2 answers simultaneously? The answer is that the radial wave, oh, that's awesome. The answer is that the radial wave function is considered so important that you often just ignore. Thanks. Oh, okay, great. Yeah, thanks. And you didn't miss anything. So I drink about 10 cups a day. So I actually do. In fact, I drink so much coffee, I don't think it affects me anymore. But okay, so the reason that there are 2 different wave functions is because of the way it's normalized. There's this one school of thought that says you should just ignore the spherical wave functions because they never really matter. And that means that, all right, so normalization means that, as I wrote this down, I'm doing R, here is phi, so we go from 2 pi, and here's theta. And as I just mentioned, R is for R, Y is for the angles. And let me put this symbol d tau, which is usually just shorthand for this. So I want you to, I use this quite a bit, you'll see it quite often. So instead of writing all this down, remember that this is a volume element because we're in spherical. Integrals, 3-dimensional integrals are really trying to calculate volume, but in XYZ it does it perfectly, but in R theta phi there's a slight error, right? And remember, that's what a Jacobian does. The Jacobian allows a 3D integral to still calculate volume, but R theta phi is a little cracked, so it needs a correction factor. Now this is d tau, so the symbol d tau is often used in place of this. I see this all the time. In fact, I think I used it in my textbook. Okay, so here's the idea. there's this one school of thought that says you should make this one, and there's this other school of thought that says, no, let's just simplify it. Let's just simplify it, and actually, so that would be 4 pi r squared. Let's just simplify it with no angles and say that this is normalized. Okay, so depending on who wrote the website you're looking at, whichever approach they used resulted in different answers, and that sucks. I cannot imagine how enraging this has made me at times when I'm trying to do calculations and nothing works. And I realize I'm using the wrong approach, and basically my wave functions aren't normalized. If my wave functions aren't normalized, nothing I'm going to do is going to work. Okay, now obviously, by the way, this is the proper one. A hydrogen atom lives in R theta phi. R theta phi. It has them. To ignore them, the theta and phi part, is ultimately incorrect. At the same time, it is true that the angle parts they hardly ever do anything. That's true, I get it, but they are still there. This is an approximation. So I try not to use this too much, although it's kind of nice. Now, it also shows you, you may recall, because I had you do this on your first homework, when you're doing three r theta phi integrals, it is the theta phi sine theta that gives you 4 pi, right? Remember r squared sine, remember how I was just saying, go from 0 to r, theta goes from, how do I do this? I have to, you have to go outer inner. Okay. And now, anyone remember what this, you actually did this. Do you remember what it is? No one? All right, you know what this 4/3 pi r cubed, you know what that is? It's the volume of the sphere. Right, so remember I just said, integrating xyz is volume. Integrating r theta phi, it should be volume, but it has a slight problem, which requires a fix-it, which is the Jacobian. And with the little fix-it, you get volume. Right, so there you go. Now the 4 pi comes about from the angles. So that's why that's there. Okay, now in the homeworks, what I have you do is I have you take, actually I give you this one, and I have you integrate it to show whether it's normalized. And what I tell you to do first, and look out for this, I always put it in the proper form. Now when it comes to hydrogen, for the most part, we're not seeing too many complex numbers. They are there. They're there for some of the angular wave functions, but the radials, there's no imaginary number. So this ends up just being r squared. Okay. Now that means that here, let's do this. And of course, our limits are 0 to infinity. It'll be 4 a naught to the 3rd power. E to the minus r is e to the minus 2r over a naught. Now, I don't think I explicitly warned you about this. But if you don't get this 2 there, you're going to screw it up. Now, what you find here in this particular one, and I think I gave you the proper identity. I did give you the proper identity. You are going to get 4 over a naught to the 3rd times, what do I have? A naught over 2. And yeah, so what do you get? You end up with 2 over a naught squared. Okay, so that sucks. So that's like the first answer. And what I then had you do is this. So let me put that in here. So again, now apparently I did not give you the, I just looked at it. I didn't give you the integral with a naught in it. I did this. Okay, so let's see here. Okay, so take out the constants. Take out the constants, and I got 2 over a to the 3. And don't let the a versus a naught fool you. A is 2 over a naught. So that means that I got 2 over 2 over 2 over 2. What is that? 8. 2, 4, 8, 8. A naught to the third. Oh yeah, look at that, that's 1. Yeah, there you go. Okay. Now you may have noticed that I did not put a 4 pi. I did not put a 4 pi. I'm just going to go ahead and answer a couple of questions. These appear several times on the homework. Why not 4 pi r squared? Where did the 4 pi go? So, and again, what I'm trying to do is make sure you really understand how these integrals work. All right, for one, this is normalized as I've done it, so that's kind of, in subsequent questions, you're going to do everything this way, and question 1 and 2 is designed to make sure you can see that. Okay, now as for the question of where is the 4 pi, right? You're probably quite used to 4 pi r squared. It doesn't appear on this homework, but why not? You're used to 4 pi r squared. The 4, not just r squared. The 4 pi is not there because now let's look at the, now this is how you properly do this, by the way. The spherical harmonics are labeled with L and M sub L. They are functions of phi and theta. And for the purposes of this homework, it is 1 over square root of 2 pi. Okay. Now this is the phi one, and this is the theta one. Now you do have to get that straight. I was pretty careful how I wrote that, but I just want you to understand that this is two-way functions multiplied. That's the phi, that's the theta. Okay, so now, again, the reason the 4 pi isn't there is because it actually represents the normalization of the angle parts. But they're going to normalize to 1. So again, so theta, sorry, I got to do this phi. Phi goes from 0 to pi. Theta goes from 0 to 2 pi. What's the way? Inner one, right? That's E. There we go. Okay, so you got to be able to take this, and now you should realize that this is 0 to pi. And then you've got 0 to 2 pi. Okay. All right, is that okay? I made a mistake. What's the mistake? Anyone see it? Remember signs and Jacobians, you gotta have this in there. That's the whole point of question 1. What mistake did I make? Huh? No, the whole point is that it's not there. Wave functions squared are normalized. Square it. See, you know how you can tell I forgot to do it? It's right here. See how this is not to be normalized. These should be normalized. That's the whole point of this. Questions 1 and 2 are about normalization. I can see immediately this isn't normalized. When you square it, that is obviously going to be normalized. And this will be 1/2. Okay. Now let's look at it. Now again, this guy ends up being, the integral of nothing is just the thing. 0 to 2 pi. Okay, ends up being 2 pi over 2 pi minus 0, so that's 1. And this ends up being minus cos over 2, 0 to pi, and I'm pretty sure that's 1. In fact, I think I have the identity, but I have it as 2. Oh, yeah. Yeah, no, that's right, I have it. That's correct. Yeah, I mentioned that it's in the cheat sheet. So look at the equations, and you'll see that I explicitly point out that this is 2. So all of this is 1, so you get 1 times 1 makes 1. Okay, so again, the reason why in question 2, in all the others, you have to multiply by r squared, but not 4 pi r squared. There's no reason for the 4 pi to be there, because that belongs to the angles. And the angles don't return 4 pi, they return 1, because they're normalized. So normally you get 4 pi, normally you get a 4 pi, because of the angle parts that are just not. In this approach, which is an approximation, there are no angles. They don't exist. So they can't be normalized. So you have to have the 4 pi. But in a proper approach, there's no 4 pi because it belongs to the angles, but the angles aren't 4 pi, they're 1. So I know it's a little bit like, but just, anyway, just try your best to let that soak in. That's why that's there. So that's questions 1 and 2. And I asked questions 1 and 2 because when you get to questions, I think it's 6, on the Zeeman effect, that's pronounced Zeeman, by the way. If you call it Zeeman, you're going to look like an idiot. So the Zeeman effect is something you're going to be analyzing with something called perturbation theory. All right, so what this is let me write that out. Perturbation theory. I didn't have time to talk about this in class because again, we're always right below graduate school level stuff, and this is kind of the graduate school level thing. And the reason is because the next stop is graduate school. So of course I'm always right below it. This is where we're supposed to end. But I did want you to see this, and it's also just good math practice. And it's just kind of interesting. I think that the way you think about this could be useful to you. Okay, so what happens is, I give you 2 different examples of a potential, and for the, oh no, sorry, I wanted to do start. Okay, that's number 7. Yeah, start is electric field. So what you're going to do is you're going to put hydrogen, you put hydrogen in an electric field. By the way, number 6, it looks hideous, but it actually ends up being really easy. Number 7 is actually quite a bit harder because you have to do a bunch of integrals. In number 6, let me give you a little hint, you actually aren't really doing any integrals. So when you look at it, you think it's going to blow your head off, and that actually ends up being really easy. Okay, the electric field generates energy by a charge, the charge of an electron times the electric field. And now electric fields are in volts. Now you heard of volts before. A volt is a joule per coulomb, and an electric charge is a coulomb. All right, so you can see how this generates energy. So joules per coulomb times coulomb. So now you're seeing how it generates energy. Yeah, but there's also a direction. And of course, it has to be an operator, which actually means nothing when it comes to positions. Derivatives are impactful, but positions really aren't. And now, the reason that this is going to get hairy, the reason I have to use the proper normalized wave functions is you have to put this in spherical coordinates, and so you're going to have yourself a integral with r and an integral with the theta part. The phi part, I'll just go ahead and tell you, I have you do it, but it actually is this. So you've seen this is part, this is 7a. You've just seen the answer to 7a right there. Okay, so anyway, now here's the deal. Perturbation theory says that you take the Hamiltonian and you have a perturbing electric field. So here's our hydrogen atom. All right, now it's in an electric field, so say plus 1 volt. That means the electron is kind of biased upwards. It kind of wants to go up because there's a positive plate that's generating a field. That's the idea. Now, quantum mechanics says that you take that hideous thing that you saw about an hour ago and make it worse. Take all that 1 over sine theta, dd theta, sine theta, dt theta, 1 over r squared, double derivative of r squared, double derivative of r, blah, blah, blah. And now add that to it and then solve. So now you got to go back to Schrodinger and tell him, all right, let's tack on something extra. Now let's see you solve it. Here's what goes down. Look through every 18th century, 19th, 20th century textbook. You do not find an answer. It is entirely possible that there are diffie-Qs that cannot be answered. Not on pen and paper. That's called an analytical solution. There are numeric solutions. There's always a numeric solution. That means that you're using supercomputers. The wave function is no longer cosine theta e to the minus r. The wave function is a giant table of numbers, which no one can really understand. Okay, so what happens is with perturbation theory is that we can add fields, electric and magnetic fields, that's in your homework, resulting in a Hamiltonian that is unsolvable. So that sucks. All right, there's no wave function, there's no energies. Okay, now here's the perturbation approach. Get rid of it and solve your wave functions. Then use expectation values to calculate what the effect of the perturbation is. Now notice I'm using psi instead of r and instead of r for the radial wave function is because, again, the reason that this question is going to kind of get you cross-eyed is because you have an r and an angle. You've got radius and theta in this question, so that's why I'm using a bigger wave function here. And I'll use a d tau. Okay, now again, the idea is that you pretend that this field isn't there. That allows us to calculate the wave functions that you just saw. And then we're going to take those energies, that minus 13.6 eV, and you're going to add whatever this does. You tack this on to the existing energies. This is the approach. Now, ultimately, this is not correct. It's an approximation. The real answer is to take the Hamiltonian, add this stuff to it, and solve from there. That's the absolute 100% correct way to do it. Problem, it can't be done. That's a big problem. So we use this approximation. If this energy is on the order of 1% of the total, it's usually like really freaking accurate. So this works really well, but it is an approximation. And so I hope you kind of see philosophically why. You're using wave functions that are not the wave functions of the full Hamiltonian. They are not the eigenfunctions of the full Hamiltonian. So that's why this is an approximation. I also want to point out another thing, that if you did, now another thing about that is, the reason why this is an approximation is if you had the full Hamiltonian and you add, say, the hydrogen 1s wave function, you do not get you do not get this. So remember, this is the eigenvalue equation. If you have the full Hamiltonian, including this electric field, and you take that e to the minus r over a naught, you do not get energy times e to the minus r over a naught. You do not get the eigenvalue equation. That's why this is not really correct. Now, I also want to point out that the reason that we're doing expectation values is because this also does not work. What I'd like to do, you know, I love eigenvalue equations. So what I'd like to do is take the wave function, have it operated on by the perturbation, this new mini Hamiltonian, and get energy, the perturbing energy, the energy of the interaction with the electric field times the wave function. And then I would just tack that on to minus 13.6, and that's what the measurement gives. It doesn't work. That's not going to happen because this wave function is not the eigenfunction of this operator. Okay, now remember that we ran into this way early in quantum mechanics when we were trying to figure out momentum of a sine wave, right? We couldn't do it. It didn't satisfy an eigenvalue equation, and that's why I told you that's why we had expectation value equations. It's done for that purpose. When you want to make an evaluation on something but the eigenvalue equation fails, the expectation value always works. So again, all right, so that's the big picture. And let me go ahead and tell you a lot about what the answers are because when you work this problem and you work it correctly, you know, it doesn't matter whether you know the answer ahead of time because all the work is the effort. You know, I don't mind sometimes giving you the answers to a question because if you just write that down again, I'm not going to give you any points, so why would I? And if you work through it, well, then you've done it. And I like to give you the answers ahead of time often, just because you know when you're done. Otherwise, you can kind of get like a little rat in one of the little wheels, because you just don't know. You know, you have a lot of insecurity. I just want you to know when you've done it right, so then you'll stop and feel good. Okay. So again, I hope I've explained why we do perturbation theory. But on number 6, you have the 1s state, which is round. And so it's like, anyway. So like here's the total wave function, and here's the electric field. Okay, now you're going to get, in this problem, 7a, you're going to get 0. And it's not going to come from the radial part, it's going to come from the angle part. When you do this, let me get you used to this. Okay, now this is theta, because theta goes from 0 to pi. Phi is 0 to 2 pi. You are going to get, what is the theta? The theta equation is this. Oh, but I forgot to, sorry. That's the left half. Here's the perturbation. Here's the right half. Okay, here, let me just go ahead and let me just write this out in full, because it's already getting kind of confusing. There we go. Okay. All right, so the way the angle parts, you're going to do the radial part, which turns into something. I don't know what, it's not 0. Then you've got the phi part, and then you got the theta part. Okay, now I already told you that the phi part turns to what every single question? Yes, 1, right? Complex conjugate times the wave function squared. 0 to 2 pi, this is clearly 1. Hopefully you have enough calculus to just see that this is just clearly the number 1. Here, let me I wrote it out that way to remind you that it's wave function, operator, wave function. Now, the perturbation of an electric field has no phi component, so it integrates to 1. So that makes perfect sense. Here, I want to make it look nice. Okay, so this doesn't do anything because it's the number 1. All right, now here. Wave function complex conjugate. Operator has a cosine, wave function, and then the Jacobian. Okay, then you look this up. Look it up on the cheat sheet. Now, I cannot dramatically emphasize that I have done quite a bit to make sure that all the things you need are in the cheat sheet, or you can use the Wolfram website. That's where I actually, when I generate the cheat sheet, that's what I use. I use the Wolfram website. This is 0. Okay, so what you get is the perturbation of a electric field on a 1s state is actually, there is none. It doesn't affect it. It makes it kind of a crappy question, to be honest, but it does introduce you to perturbation theory, and you can kind of do it. But now, why is it 0? And of course, the next question, it isn't 0. You can think of it this way. Remember that the electron is attracted, to, there's some like positive plate at some positive voltage above the hydrogen atom, and then there's a negative bias to a plate below it. So it's in an electric field. Now you can think of the electron as it's whizzing around. When it's here, it's bad. When it's up here, it's good. Right? It likes to be up here, it doesn't like to be down there. However, because the wave function doesn't change due to the electric field, because of our perturbation approach, it spends just as much time towards the plate as it does, the good plate, as it does towards the bad plate. So, good energy, bad energy. But the wave function says that both are possible, equally possible. It spends just as much time towards the positive plate as it does towards the negative plate. And recall also that this is, how do you draw a field? It's like this, something like that. So anyway, right, it can't really interact. So there's no interaction energy. So that's why that comes out the way it does. I know it's kind of unsatisfying, but that is how it works. Now, to give you something that's actually not so crappy, and again, as I mentioned, that we're always approaching graduate level stuff, I gave you an example where there is an energy interaction. Now, what happens is, though, all right, what I just described here will happen for every state, 2s, 2p, 3s, 3p. By themselves, the wave functions don't interact, the hydrogen atom doesn't interact with an electric field. But what the electric field does, and I show grad students how to do this, I'm not going to show you, I just want you to know that this is how it goes. You take a 2s, so what happens is, so let's do a 2pz. What the electric field does is it mixes states together. It mixes the 2s and the 2p. Now the reason that works is, now remember all this phase stuff? When you add these together, and I could use a computer to plot it, but I won't, it looks like this. And of course here's, the nucleus is right here, right? So again, for reasons I'm not describing, the math reasons, the electric field takes these two wave functions and says, well, the new state is now the sum of these two. Now the reason that matters is, trying to make that all look 3D. Now look at this electric field, right? Now we're going to add a plate. Well, we've already added a plate. And so we've got a positive voltage plate on top, got a negative voltage plate on bottom. Remember, negative voltage is repulsive to an electron. You see, the electron now spends more time up. It is now spending more of its time towards the positive plate. Now you can also think of this another way if you're really savvy with your physics. It's also formed a dipole, so it interacts with the field. Dipoles interact with the field. That's another way to think about it if you are really up on your E and F. Okay. So that's what this perturbation does. Now, I don't have you do this math part. Again, I do that in my grad level class, but what I have you do is calculate the interaction energy. The way that this one ends up going is you take the 1s wave function, and then those constants go on the outside, and this is just the electric field strength. And I even have you plug in a number. You'll actually plug in numbers to this. And you plug in like 3 to the 6 volts per meter. That's like the strongest electric field that you could create. And then you end up with again, there's the complex conjugate doesn't do anything. Uh-oh.